We're looking at a shorter video, fall-up temperature. This is salinity structure from the Buzzards Bay model. Results again over September 30. Same transect from temperature. Cross Bay. This is the west side of the bay. This is the east side of the bay, or mainland and island side. If I put a line from surface to bottom through the bay, it results in something like this. So at the surface on the left, bottom on the right, and we have, it goes roughly from, unfortunately this gets scaled by my stretching factor here, but surface to bottom we have lower salinity water at the surface and higher salinity at the water at the bottom, but it's pretty weak. Most of the gradient's in the lateral direction because you have fresh water introduced in the rivers along the side of the bay here. And just like in the case of temperature, the strong mixing with Vineyard Sound, which was more reflective of open ocean salinities and temperatures, and mixing with Rhode Island Sound through the mouth of the bay, which is reflective of of shelf temperature and salinities, results in the deeper waters or east side of the bay having more open ocean, or shelf I should say, characteristics. So in this case, you have the higher salinity water over here in the deep water near these holes and open ocean, and again the fresher water in the upper part of the bay. So it's the inverse in some sense of the temperature, because we had warmer, higher temperatures in the bay. Here we have lower salinities, but again they have opposite controls on the density, don't forget. So give me this big lateral gradient, less in terms of a top to bottom gradient than we saw in the temperature case. But temperature, of course, is influenced by large surface exchanges of that quantity, diurnal heating. So you have different dynamics there. If I put a probe somewhere in the middle of the bay, and we can look at the time series of salinity, surface salinity at that point, we essentially have the same thing what we saw in temperature. As it floods in, here the salinity is going up, the temperature went down, but that's reflective of the properties of the open ocean intruding into the bay. And then on the ebb, the upper bay water is now crossing that point, and it's reducing the reducing the salinity. And then we come back again, and we have open ocean properties coming in, and then bay properties coming back down. So it's very much in tune with what we saw with temperature. And again, it's not periodic. It doesn't return to the same value, which means that it's changing throughout the day. In temperature, we could suspect heat flux, although it was cooling over the course of the day, and it was quite a warm September day. But in this case, we're seeing the same thing happening. We're seeing a strengthening of the salinity over the course of the day. So it's creeping towards ocean characteristics, and this has to do again with this sort of idea of the two-way flow. There we're exporting Buzzards Bay water and importing the open ocean water, which is modifying the properties locally. I think that's all I want to say about salinity. So we'll look again at observations. I can see here that the salinity here is less than it was in the observations. And again, as I mentioned in the temperature video, there isn't good data to assimilate in terms of salinity, and so getting salinity correct over a long period is quite difficult. One of the important things is that it's not as much the magnitude of salinity as important as the gradient in salinity. So having these key open ocean Buzzards Bay gradients, getting those correct is really critical, because it's gradients that drive flows. Absolute values are more important to decide whether or not a fish larvae can survive or not, these kind of things. So that's all for that.